All right, Miss Teasley here. We are going to talk about exponential functions. All right, so an exponential function is a function in this form. You have a base, which in this case they have a base a. I say a represents any number. The number has to be greater than 0, and the number a cannot equal 1. The way that you know that you're dealing with an exponential function is if you have a variable x as an exponent. So whenever you see the variable x in your exponent, you know that you're dealing with an exponential function. All right, so start with the first example. We're just evaluating an exponential expression. They tell us that f of x equals 4 to the x, and they want us to find the following function values. So to find f of negative 2, so I have f of x equals 4 to the x power. So in place of x, everywhere I see an x, I'm going to replace the x with negative 2. So negative 2. All right, and then I want to simplify this right side. Whenever you have a negative exponent, you can take the reciprocal to get rid of that negative exponent. So this becomes 1 over 4 to the positive 2. And 1 over 4 squared is 1 over 16. All right, so that's the value for f of negative 2. The rest of these, I'm going to show you how you can just throw this into decimals to get your final answer. Remember, function values are y values, so we're actually looking for the y values when x equals what's inside the parentheses. So let's put this into decimals. So the first one I have is f of x. I'm going to use function notation. So f of x equals 4 to the x power. So that's the graph of the function. The first one we did was the f of negative 2. The next question said find f of 5. So you can use function notation and actually just type in f of 5. So I'm going to go back and put f parentheses 5. And that's my function value. My function value when f is 5 is 1024. So you can go ahead and jot that down. Another way that you can do this without doing function notation, you can go back to the original function, which is in this first box. Hit the gear button at the top right. And then I'm going to hit this table. So what it does is it changes my function into a table. And you're looking for the y value. So the numbers inside your parentheses are your x values. So they already populated some numbers in the table. I'm just going to write over these numbers. I want to know the value for f of 5. So I'm just going to type 5 here. And notice how that 1024 pops up. And let's just go ahead and do the other two. 2 divided by 3. Oops. So I'm going to go down to the next box and just type over this. 2 over 3. All right, you have that decimal. And then you have 2.5. So 2.5. All right, so at 2.15. All right, there's your decimals. And one thing I like about decimals, if you actually, when you use this table, they actually plot the points and you can label them by touching on each point. All right, so that was the first example. All right, next we're going to look at exponential functions, looking at it in a graph form. In this first box, this box represents exponential growth. And what we see pictured here is the graph for f of x equals 2 to the x power. So in this case, our a value or our base is 2. So a equals 2. And what they have listed over here, right, on this graph, you see these 3 points. Whenever you graph an exponential function, these 3 points will always lie on your exponential function graph. So it's helpful. I'm just going to darken the points. So whenever you do -1, whenever you find the function value at -1 or the y value at -1, it's going to be 1 over a, which is the reciprocal. All right, so 1 over a is the reciprocal of a. And if you plot the point 0, At x equals 0, your y value will be 1. And then when you plot the y value, when x equals 1, you're going to get the actual a value, which is 2. All right, so let's kind of check this over here. I'm going to do a table, even though they have the values here. As a matter of fact, they have them over here. So at -1, notice how when x equals -1, the answer is 1 over 2, all right, which is the reciprocal of a. So I'm going to make a note, this is the reciprocal of the base. Right. At 0, the y value is 1, and at 1, your y value is 2. 2 is your a value. We're going to actually use this to sketch some graphs, and this is when you have an exponential function in this form. The domain of this graph is all real numbers, so it goes from -infinity to infinity. Your range, if you look at this graph, coming from, I'm going to start from the right side. If you sketch this graph, this is exponential growth, but if you look here, the graph gets closer and closer to the y value, but it doesn't ever hit, it gets closer and closer to the x-axis, but it doesn't actually cross over the x-axis. It gets closer and closer to a y value of 0. So the range for this graph will be parentheses, because 0 is not included, 0 to positive infinity. So that's the range of this graph. Anytime your a value is a number that's greater than 1, this is exponential growth. All right, exponential growth, if you trace this graph coming from left to right, so I'm going to go back from left to right, same thing, it works like increasing and decreasing functions. If you trace this graph from left to right, you're increasing. All right, so this is growth. In this case, your x-axis is the horizontal asymptote, and then the graph passes through the points. So here are these 3 points that we're going to use to help us sketch a graph later on, but it passes through the point -1, 1 over a, 0, 1, and 1a. So that's for exponential growth. Moving on, in this next box, we have an example of exponential decay. So exponential decay. In this example, a is 1 over 2. So if you go back, we're going to look at those 3 points that lie on this graph. So you have the point -1 and 1 over a, again, which is the reciprocal of a. And then you have 0, 1, and 1a. So let's check this in this table. So they already gave us the table of values. So notice how when x equals -1, my y value is 2. 2 is the reciprocal of 1/2. So again, just like before, this is the reciprocal. 0, 1, and then 1, and then the a value, which is 1/2. So those 3 points always lie on your exponential functions that's in this form, a raised to the x power. The domain of this graph is the same. It goes from -infinity to infinity. The range is also the same. It doesn't actually ever hit the x-axis. It gets closer and closer to it. So the range is from 0 to positive infinity. Whenever your a value falls between 0 and 1, all right, it can't be less than 0, but anytime you have an a value that's less than 1, this is exponential decay. Again, the x-axis is a horizontal asymptote. The graph passes through the 3 points, -1 and 1 over a, 0, 1, and 1a. All right, well, we're going to do an example. We're going to actually sketch the graph. I'm going to change this a little bit. We already graph f of x equals 1 over 2 to the x power. So let's change it. And I'll make this f of x. Let's do f of x equals 3 to the x power. All right, so I'm changing this example because they already have the graph sketch for 1/2 to the x power above. So looking at this function, this new function that I created, f of x equals 3 to the x power. In this example, a equals 3. Because 3 is a number that's greater than 1, this is going to be exponential growth. So my graph should look something like this. And then I'm going to use those 3 special values to help me plot some points on this graph so I can sketch it. So remember, the points are -1, comma 1a, 1 over a. Then I have the point 0, 1 and the point 1a. So here, x and y column, at -1, it should be the reciprocal of a, where the reciprocal of a is 1 over 3. When x equals 0, the y value is 1. And at 1, I should get my a value, which in this case is 3. So using these 3 points and what I know about exponential growth, I should be able to sketch the graph of this. So at -1, we'll say this is about 1/3 here. So we'll put a point here. At 0, the point is 1. And at 1, 3. So 3 will be about, we'll say it's here. So at 1, 3. So using this, what we know about exponential growth, the graphs look something like this. All right, it gets closer and closer. All right, and they didn't give us enough space because it was supposed to be a decay problem. But that's how your graph will look. Similar to that. So when it comes down to you doing your assignments in my math lab, when it comes down to sketching the graph or graphing, using a graphing tool, just use the 3 points that we have listed here, the -1 and 1 over a. Again, that's the reciprocal of the a value, 0, 1, and 1a. All right, next we'll look at solving some exponential equations. I'm going to use a method called Equate the Bases. So equate the basis. So you're trying to solve this equation. Whenever you're solving an equation, you're trying to get x by itself. So what I'm going to do is I'm going to rewrite this problem. My goal is to get that exponent. Now, what is the actual value for x that would give me 1 over 125? Well, remember, I can just rewrite this. And this is going to be 1 over 25 is the same thing as 5 to the 3rd power. So that's where that equating the base comes from. So you want to rewrite both sides of your equation using the same base. So I was able to rewrite 125 as 5 to the 3rd power. You don't want a fraction on the side. You want both sides to look identical. So you want to write this as 5 to the x equals, to get rid of that fraction, I'm going to make it 5 to the -3rd power. So you want both sides of the equation to look identical. And if you notice, on the left side, I have 5 to the x power. This equals 5 to the -3rd power. So then my question is, well, what's the value of x? To make both sides equal, that means x will have to equal -3. So whatever you have, once you equate the bases, you just bring it down. So x equals -3. That's your value for x. So we're going to use this to solve. I'm going to actually do the example here, and then we'll do one more. I'll give you one to try where you can pause the video and try it. So here, 3 to the x plus 1 equals 9 to the x minus 3. We want to equate the bases. Well, this is 3 to the x plus 1. I can rewrite this 9 using 3 squared. So 9 is just 3 squared. But I can't forget that I still have that x minus 3 as an exponent. So what you want to do is you want to keep x minus 3 as an exponent. You want to put it right beside that 2 in parentheses. So that's where that x minus 3 goes. So again, this 3 squared is equivalent to 9. And if you notice, both sides of the equation, they have a base of 3. So now that I have a base of 3 on both sides, all I need to do is drop the base and set exponents equal to each other. So at this point, I have x plus 1 equals 2 parentheses x minus 3. And this is the equation that you're actually going to solve. So drop the base, set exponents equal, and then solve. So this is what I'm going to solve, and that's going to give me my final answer. So when I solve this, I'm just going to rewrite it over here for more space. X plus 1 equals 2 times x minus 3. X plus 1 equals, I'm going to distribute this 2 to this parentheses. So this is 2x minus 6. My goal is to get x by itself. So I'm going to just subtract x from both sides here. All right, I want to keep my x positive. So on the left side, I still have that plus 1 or positive 1. 2x minus x is just x. Bring down my negative 6 or minus 6 behind this. Again, I want x by itself. So now to get rid of that minus 6, I'm going to have to add 6 to both sides. And so 1 plus 6 equals 7. So that is your value for x. All right, so you try. Let me give you an example to try. Try 4 to the x plus 1 equals 8 to the 2x minus 3. All right, so this will be a problem where you can pause the video, stop, try it, and then we'll come back together and work it out. All right, so hopefully you had a chance to try this example. So again, we're going to use Equate the Basis to solve this problem. So I have to ask myself, well, what base could I use to rewrite both the 4 and the 8? Well, I can't use 4 because I can't do 4 to any power and get 8. 4 squared is 16, it's not 8. But what I can use 2 to rewrite both numbers. I can rewrite 4 as 2 squared, and I can rewrite 8 as 2 to the third power. So this is 2 squared. But remember, I still have that exponent of x plus 1 there beside it. So I'm going to write that as an exponent right beside that 2 equals 8 is 2 to the third power. And then in parentheses right beside that 3, I'm going to bring down my 2x minus 3. So now that both now that both bases are the same, I drop the bases, so you no longer need the 2. You're only going to deal with the exponents. So what I have as an exponent on the left side is 2 parentheses x plus 1. And on the right side, I have 3 parentheses 2x minus 3. And this is what you solve to find your final answer. So I'm going to distribute 2 to what's inside this parentheses. This is 2x plus 2. 3 times 2x is 6x. 3 times negative 3 is negative 9. Again, my goal is to solve for x. I'm going to subtract 2x from both sides. All right, on the left side, I still have this plus 2 or positive 2 equals 6x minus 2x is 4x. Bring down my minus 9. I want to get rid of that minus 9 so I can get my x by itself. So I'm going to add 9 to both sides. 2 plus 9 is, I'm going to come down here and make it 11 equals 4x. And then divide both sides by 4. So x equals 11 over 4. All right. Moving on to example 5. Solve an equation with a fractional exponent or rational exponent. My goal is to get x by itself. So x to the 2/3 equals 251. Well, to get x by itself, all I need to do is to get rid of that 2/3. Well, what number can I multiply by 2/3 to get rid of it? And the answer is the reciprocal. So I'm going to rewrite this. Let me move this down a little bit. I'm going to raise both sides to the 3/2 power. So what I do to one side, I got to do to the other side. And the reason why I chose to raise it to the 3/2 power is because when you raise a power to a power, you're multiplying. And when you multiply reciprocals, you get 1. So 2 to the 3rd times 3/2 is 1. So I have my x by itself. And then the answer to this, 251 to the 3/2. All right, this is not a perfect answer. So I'm just going to write it as 3/2. All right, I'm assuming, all right, I'm going to rewrite this. I'm going to rewrite this problem. I'm assuming that this might have been a typo. So let's cross out. Let's make this 25 instead of 251. All right, so I'm going to erase this and I'm going to rewrite this. I'm going to rework this problem using 25 versus 251. All right, so I just quit that. I think that's a typo. So going back to the beginning, I have x to the 2/3 this time equals 25. Again, my goal is to get that x by itself. So I'm going to raise this side to the 3/2 power, which is the exponent. What you do to one side, you got to do to the other. On the left side, the exponents cancel out, so you get x equals 25 to the 3/2. Well, when I rewrite this, this is the same thing as the square root of 25. All right, that's what that 2 does. It takes the square root. And whatever I get for that answer, I raise to the 3rd power. So that's where the 3 comes. The 3 is on the outside. The square of 25 is 5. 5 to the 3rd power is 125. All right. Now we'll talk about compound interest. All right. So in this box, it explains compound interest. Let me give you the formula for compound interest. The formula for compound interest is A equals P parentheses 1 plus R over N to the NT power. All right. So if P dollars are deposited in an account, so P is what you deposit into this account, or P stands for principal initial value. That's what you're depositing. Annual rate of interest is R. All right, so this is your APR. R is your APR. Compounded N times per year. All right, the number of compounding, the N values have, the number of compoundings each have different N values. So meaning that when you see this in a word problem, it's not going to say compounded, N equals 2. They'll use words like monthly. All right, so the number of compoundings. So let's see compoundings. So if you see the word monthly, well, how many times in a year would that be? That would be N equals 12. If you see semi-annual, that's twice a year. So think about those semi-annual sales. And then something like quarterly, N equals 4. All right, so 4 times a year. So you have to know what N value to use based on what the word problem says. T is going to be the number of years. All right, so after T years in the account. So T years. All right, so let's look at an example. So using a compound interest formula, suppose $2,500 is deposited in an account paying 3% interest per year, compounded semi-annually. They were nice and they told you that's twice per year. All right, but if you didn't know, they didn't give you that information, you would need to know that semi-annual is twice, or N equals 2. So let's write down the information that we have. So first of all, this 2,500, this is P. So P equals 2,500. The R value, the interest rate, you don't use 3%. You have to change it to decimal form. So the word percent means per 100. So if I take my R and do 3 over 100, I will get 0.03. So the 0.03 is what I'm using. And then compounded semi-annually, N equals 2. So it says find the amount in the account. So that's going to be your A value, the accumulated amount, after 10 years with no withdrawals. So in this case, T equals 10. And so you put this all into this formula. All right, remember the formula is A equals P, 1 plus R over N to the NT. My P value is 2,500. 1 plus R is 0.03 over N is 2. And then my exponent is 2 times T. T is 10, so this is times 10. I'm going to put that right into my calculator, and it'll give me my final answer. So let's see. 25. So to get my value, my accumulated amount, 2,500. Parentheses 1 plus, hit the division bar so you can get your fraction, 0.03. The number of compounds was 2. Come out here on the outside, exponent is going to be 2 times, all right, we want this to be as an exponent. So let's see, we might have to put that in parentheses. So exponent, parentheses, 2 times 10. Or just change it to 20. All right, so 2 times 10 or just 20. So we're talking about money. So money, you want 2 decimal places. So 33, 67, 14. All right, so this is 3367.14. So this is how much that you have accumulated over the 10 year. It says how much interest is earned over the 10-year period. Well, to find out how much interest is earned, you start off with $2,500. So you're going to take the accumulated amount. All right, so 3367.14 and subtract the initial amount, which is 2,500. And that's going to give you how much interest was earned. So let's subtract 2,500 from this. So I go down here, 3367.14, subtract 2,500. You have accumulated $867.14. All right, the number E in continuous compounding. So you have this new value, or this value E. E actually has a value. It kind of works like pi. Pi has that value 3.14. Well, E has a value attached to it. So let's put this into decimal so you can see the value of E. So if I go to, let's see here, let's see what it, so here's my value for E. E is this 2.7182818. All right, that's my value for E. So E actually has a value to it. So I'm just going to write down 2.71828. So 2.71828. All right, but you'll just use the E button that's in your calculator. So that brings us to this continuous compounding. So I just introduced the compound interest formula. So that's the formula that you're going to use when they say compound interest. Now, I gave you the different values of compoundings. Now, if you see the word compounded continuously, you have to use a total different formula. So this only applies when the word problem says compounded continuously. So when it says compounded continuously, there's no n value. You have to use this formula, A equals PE to the RT, or A perk. This is the only time you use this formula. You only use it if you see the word, and looking at an example below, compounded continuously. So suppose $8,000 is deposited into an account. So my P value is 8,000. The account is paying 5% interest. So my R value is the 5%, or 5 over 100, which is 0.05, for 6 years. T equals 6. Find the total amount on deposit at the end of 6 years if it's compounded continuously. So because it says it's compounded continuously, I have to use this formula. All right, plug in my values in, 8,000. E, remember E is already in your calculator. The value for E is already there. R would be 0.05 times 6. So that's what I'm going to put into Desmos to get how much I accumulated after 6 years, or over that 6-year period, if it's compounded continuously. So 800. And then you just go to your keyboard and use the E button, right, if you're using Desmos. The exponent would be 0.05 times 6. So you'll want to put that in parentheses, 0.05, and then times 6. So that's the balance after that 6-year period. $1,079, and you will round it up to 89 cents. So $1,079.89. All right, that's it.